In this paper, we propose the real-time detection transformer, called RT-DETR, the first real-time end-to-end object detector. Now, we present an example to demonstrate the excellent real-time detection performance of RT-DETR. The proposed RT-DETR not only outperforms the previously advanced YOLO detectors in both speed and accuracy, but also eliminates the negative impact caused by NMS post-processing on real-time object detection. Specifically, our RT-DETR R50 achieves 53.1% AP on CocoVal 2017 and 108 FPS on T4 GPU, while RT-DETR R101 achieves 54.3% AP and 74 FPS, outperforming L and X models of previously advanced YOLO detectors in both speed and accuracy. We also develop scaled RT-DETRs by scaling the encoder and decoder with smaller backbones, which outperform the lighter YOLO detectors. Furthermore, RT-DETR R50 outperforms Dino-deformable DETR R50 by 2.2% AP in accuracy and by about 21 times in FPS, significantly improves accuracy and speed of DETRs. Compared to previously advanced real-time object detectors, our RT-DETR achieves state-of-the-art performance. The YOLO series has become the most popular framework for real-time object detection due to its reasonable trade-off between speed and accuracy. However, we observe that the speed and accuracy of YOLOs are negatively affected by the NMS. Recently, end-to-end transformer-based detectors, DETRs, have provided an alternative to eliminating NMS. Nevertheless, the high computational cost limits their practicality and hinders them from fully exploiting the advantage of excluding NMS. In this paper, we propose the real-time detection transformer RT-DETR to addresses the above dilemma. However, solving this problem is non-trivial. We build RT-DETR in two steps, drawing on the advanced DETR. First, we focus on maintaining accuracy while improving speed, followed by maintaining speed while improving accuracy. Specifically, we design an efficient hybrid encoder to expeditiously process multiscale features by decoupling intrascale interaction and cross-scale fusion to improve speed. Then, we propose the uncertain to minimal query selection to provide high-quality initial queries to the decoder, thereby improving accuracy. NMS is a widely used post-processing algorithm in object detection, employed to eliminate overlapping output boxes. Two thresholds are required in NMS: confidence threshold and IOU threshold. Specifically, the boxes with scores below the confidence threshold are directly filtered out, and whenever the IOU of any two boxes exceeds the IOU threshold, the box with the lower score will be discarded. This process is performed iteratively until all boxes of every category have been processed. Thus, the execution time of NMS primarily depends on the number of boxes and two thresholds. To verify this observation, we leverage YOLO v5 and YOLO v8 for analysis. We first count the number of boxes remaining after filtering the output boxes with different confidence thresholds on the same input. We sample values from 0.001 to 0.25 as confidence thresholds to count the number of remaining boxes of the two detectors and plot them on a bar graph, which intuitively reflects that NMS is sensitive to its hyperparameters. As the confidence threshold increases, more prediction boxes are filtered out, and the number of remaining boxes that need to calculate IOU decreases, thus reducing the execution time of NMS. Furthermore, we use YOLO v8 to evaluate the accuracy on the COCO-VAL 2017 and test the execution time of the NMS operation under different hyperparameters. From the results, we can conclude that the execution time of the efficient NMS kernel increases as the confidence threshold decreases or the IOU threshold increases. With a confidence threshold of 0.001 and an IOU threshold of 0.7, YOLO v8 achieves the best AP results, but the corresponding NMS time is at a higher level. To enable a fair comparison of the end-to-end speed of various real-time detectors, we establish an end-to-end speed benchmark. Considering that the execution time of NMS is influenced by the input, it is necessary to choose a benchmark dataset and calculate the average execution time across multiple images. We choose COCO-VAL 2017 as the benchmark dataset and append the NMS post-processing plugin of TensorRT for YOLO detectors as mentioned above. We use Dino deformable R50 with the smaller size data reader and lighter decoder used in RT-DETR for experiments and first remove the multi-scale transformer encoder in Dino deformable R50 as variant A. Then, different types of the encoder are inserted to produce a series of variants based on A. Specifically, variant B inserts a single-scale transformer encoder into A, which uses one layer of transformer block. The multi-scale features share the encoder for intra-scale feature interaction and then concatenate as output. Variant C introduces cross-scale feature fusion based on B and feeds the concatenated features into the multi-scale transformer encoder to perform simultaneous intrascale and cross-scale feature interaction. Variant D decouples intrascale interaction and cross-scale fusion by utilizing the single-scale transformer encoder for the former and a pianet-style structure for the latter. Variant E enhances the intrascale interaction and cross-scale fusion based on D. The indicators of the set of variants are shown in this table. From A to B proves that the intrascale feature interaction is significant, but the single-scale transformer encoder is computationally expensive. From B to C shows that the cross-scale feature fusion is also necessary, but the multi-scale transformer encoder requires higher computational cost. From C to D suggests that decoupling intrascale interaction and cross-scale fusion not only reduces computational cost but also improves accuracy. From D to DS5 demonstrating that intrascale interactions of lower-level features are not required. Note that DS5 represents the intrascale interaction only on S5 in variant D. Based on the above analysis, we rethink the structure of the DETR encoder and design an efficient hybrid encoder to replace the vanilla transformer encoder, which significantly improves inference speed by decoupling the intrascale interaction and cross-scale fusion of features with different scales. The proposed hybrid encoder consists of two modules, namely the attention-based intrascale feature interaction and the CNN-based cross-scale feature fusion. Specifically, AIFI further reduces the computational cost by performing the intrascale interaction only on S5 with the single-scale transformer encoder. CCFF is optimized based on the cross-scale fusion module, which inserts several fusion blocks consisting of convolutional layers into the fusion path. The role of the fusion block is to fuse two adjacent scale features into a new feature. The fusion block contains two 1x1 convolutions to adjust the number of channels. N rep blocks composed of rep convolution are used for feature fusion, and the two path outputs are fused by element-wise add. To reduce the difficulty of optimizing object queries in DETR, the query selection is proposed, which selects the top K features from the encoder to initialize object queries according to their confidence scores. However, the detector are required to simultaneously model the category and location of objects, both of which determine the quality of the features. The current query selection lead to a considerable level of uncertainty in the selected features, resulting in suboptimal initialization for the decoder and hindering the performance of the detector. To address this problem, we propose the uncertainty minimal query selection scheme, which explicitly constructs and optimizes the epistemic uncertainty to model the joint latent variable of encoder features, thereby providing high-quality queries for the decoder. Specifically, the feature uncertainty is defined as the discrepancy between the predicted distributions of localization and classification. To minimize the uncertainty of the queries, we integrate the uncertainty into the loss function for the gradient-based optimization. To analyze the effectiveness of the uncertainty minimal query selection, we visualize the classification scores and IOU scores of the selected features on COCO-VAL 2017. The purple and green dots represent the selected features from the model trained with uncertain to minimal query selection and vanilla query selection, respectively. The most striking feature of the scatter plot is that the purple dots are concentrated in the top right of the figure, while the green dots are concentrated in the bottom right. This shows that uncertain to minimal query selection produces more high-quality encoder features. From the results, our RT-DETR R50 and RT-DETR R101 outperforms the state-of-the-art L and X models of YOLO detectors in both speed and accuracy, and greatly improve the efficiency and performance of DETR detectors. Ablation study on query selection shows that the encoder features selected by our uncertain to minimal query selection not only increase the proportion of high classification scores, but also provide more high-quality features, thereby improving the performance. Ablation study on decoder shows that RT-DETR supports flexible speed tuning by adjusting the number of decoder layers without retraining, thus improving its practicality. Furthermore, the surprising improvement per trained on objects 365 further demonstrates the potential of RT-DETR and provides the powerful real-time object detector for various real-time scenarios in the industry. To adapt to diverse real-time detection scenarios, we develop lighter-scaled RT-DETRs by scaling the encoder and decoder. The results shows that our scaled RT-DETRs outperform the lighter YOLO detectors in both speed and accuracy by simple scaling. To intuitively demonstrate the impact of post-processing on the detector, we first visualize the predictions produced by YOLO V8. The higher the confidence threshold, the more prediction boxes are filtered out and the number of false negatives increases. However, using a lower confidence threshold results in a large number of redundant boxes and increases the number of false positives. In addition, the higher the IOU threshold, the fewer overlapping boxes are filtered out in each round of screening, and the number of false positives increases, as shown in the position marked by the red circle. Finally, we present the visualization of RT-DETR. In complex scenarios, RT-DETR demonstrates its capability to detect diverse objects, even when they are small or densely packed, such as cups, wine glasses, and individuals. Moreover, RT-DETR successfully detects objects under various difficult conditions, including motion blur, rotation, and occlusion. These predictions substantiate the excellent detection performance of RT-DETR. Thanks for watching.